Welcome back, guys. Last time we were talking about the simplest form of variable selection heuristic, which was min-dom. It espoused the first failed principle, but now we're going to look at a number of augmentation of that simple heuristic, and we'll start with things that make use of degrees. Now, degree-based heuristic, the idea is that if a variable is appearing in many constraints in the graph that represents the constraints in the variable, its degree is going to be higher, and if it's connected to many constraints, if you fix it, you're likely to trigger a lot more propagation than a variable that is somewhat isolated. In the extreme case, a variable that's not touching any other, it's not constrained, fixing it won't do anything to solve your problem. So you shouldn't be doing that first. The idea is branch first on the things that are highly connected. And we're going to look at several variants that are increasingly more involved. Now, the first one is basically the degree of the variable, simply being the number of constraints that touch it. That's the first heuristic. We're going to call it h0. The next one is going to be h1, dom plus dog, and then dom over dog, which are two extensions. But let's start with the degree. And what you see down here is a constraint graph, right? It's a simple constraint graph. And you notice that if it's just this equality, saying, for example, x1 is not equal to x2, as the edge connecting these two variables, we see that variables have different degrees because x2 here can't be equal to x1, can't be equal to x3, and it can't be equal to x4. So it has a degree 3. Likewise, x3 has a degree 2, x4 has a degree 3, x5 has a degree 1. The basic idea is branch on something that has a high degree, like x2 or x4. These variables have a high degree, and because it's a disequality, let's say that when you fix x4, what's going to happen if you fix it to value 1 is that value 1 is going to disappear from the domain of x2, the domain of x3, and the domain of x5. You have a lot of propagation as a result when you do that. Whereas if you were to fix, say, only x5 to 1, the value 1 would disappear from x4, but when this happens, it doesn't allow you to necessarily draw inferences on the two other variables, and the propagation stops there. So try to promote propagation by fixing variables that have a high degree. That's the basic idea behind h0. Now, the idea of h1 and h2 are basically to take the best of both worlds. We've seen that selecting variables that have the smallest domain is a good idea. We've seen now that fixing variables that have a high degree is a good idea. So what could we do? h1 is blending the two by saying, well, first we'll go by variable that have the smallest domain. We'll do min-dom. But if I find out that three variables have the same domain size and I don't know which one to pick, the one I will choose will be the one that has the highest degree. That is your breaking ties based on the degree after doing your minimum domain size selection. And that can work quite well. The other option, of course, is to say, wait a minute, what I could do is consider variables that have a small domain, so I'm going to minimize the size of the domain, but I don't want to just sequence the two decisions, do first domain and degree. Instead, I'm going to say that if the degree is big, and I use the fraction dom divided by dog, the bigger the degree, the smaller the fraction. Therefore, variables that have high degree will make the fraction smaller. So if I select the minimum of the ratio, I'm basically compounding the two at the same time. I'm never ignoring dog until the domain have equal sizes. I'm taking it into account all the time by looking at the ratio. Now, you notice that if a degree is very low, this, like degree 1, this degenerates in just being the dom heuristic, and the domain size, since we're minimizing the ratio, is still capturing everything that we want to do. So that's the three first alternative. But people thought we can probably do better than that. And here comes heuristic 3, called weighted degree. Now, the idea here is a little bit more involved because we wish to introduce the idea of learning what has turned out to be complicating or difficult variables over time. And the idea is that each time we are going to encounter a failure in a constraint, we're going to increase the weight of the constraint by 1 to convey that failure to convey that this is a difficult constraint. So just imagine that. Every constraint has a counter, they all start at 0, and as constraints fail, their counter starts going up for the one that detected the failure, right? So that's the basic idea. With the premise, of course, that if a constraint has failed in the past, it's going to fail again. It has been difficult in the past, it will be difficult in the future. Consistency, right? Now, how do we get a heuristic out of this? Well, the trick is to think of weighted degree of a variable x being simply the sum of the weights of the constraints that appear on x and that have still a variable that's not fixed. So that's wdug, and we're going to use the same kind of an idea of dividing dom by dug, but now dom by wdug. So we're going to take the ratio of the domain size over that weighted degree, right? So that's the interesting part. And the weighing is based on how often the constraint is responsible for failures. Now, the weakness, of course, is that a constraint that fails may not be the only guilty party for causing the failures. There might be other constraints that do this, but the whole point is that the propagation will capture that in the fixed point algorithm, and we will get somewhere, maybe not as far as we want, but we'll manage to do something. So dom wdug is not implemented in minicp, but the good news is that it's a wonderful exercise, as you can imagine. It's quite easy to do. There are a couple of prerequisites. The first thing is that you're going to need to add a counter, nf, which is the number of failures attributed to a constraint. You would put that in, say, the abstract constraint, which is an abstract class, where each time the constraint fails, we're going to up that counter. You would add a method cstr constraint on the variable in order to retrieve the list of constraints that use the variable, right? To know how many you have. Then you could add the method dynamic degree to the constraints that tell you the number of free variables. That is the number of variables that are not fixed yet. So this is a subset of the variables of the constraint. It's those that are not fixed. Now, of course, we need to update the counter nf whenever the propagation has detected an exception, a failure, right? Because we have an inconsistency. So when an inconsistency is picked up by the propagation, it should grab the constraint that caused it and up its nf counter by 1. Now, to build a heuristic, we just need scoring. And we have all the ingredients to do it. The scoring method for a variable is based on the failures that are present in the network. So we're going to make use of x.cstr to retrieve the constraints of the variable x and be able to loop on them. And we're going to say that the score of a constraint is what? It's basically the number of failures multiplied by its dynamic degree, that is the number of unbound variables, minus 1, because we should have at least 1, and that should be positive. So if there is at least 1 unbound variable in the constraint, beyond the one that we're looking at, we're going to actually pick up the number of failures. That's the score of the constraint. Now, the score of the variable is a fraction, once again. It's basically the one we see here. It's the domain of the variable. So smaller domain is something that's preferable, right? Divided by the sum of the score of the constraint. Your best variable is one that's going to actually minimize this score, right? So the best variable x star is the one that makes this as small as possible. Why? Because a smaller domain makes the fraction smaller, and if the score increases, that is, if there are lots of failure caused by several constraints, the score is going to climb, and that's going to make that ratio even smaller. So by picking the minimum one, we favor the variable that appear in constraints that tend to wreak havoc and cause failures. That's the whole idea. That's the whole point of dom wdug. Now, next time, we will be looking at another class of variable selection heuristic, but this is a story for the next video. See you then.